Hi friends, good morning. Today we are going to discuss about hardwired control. Okay. In order to execute the instruction, the processor must have some means of generating the control signals. So, in order needed in the proper sequence. Computer designers use a wide variety of techniques to solve this problem. The approaches used fall into one of two categories. Those are hardwired control and second one is microprogrammed control. Consider if we consider a sequence of control signals. Each step in this sequence is completed in one clock period. So each and every step will be executed in one clock period. Okay, so a counter may be used to keep track of the control steps. Okay, so which is shown in this figure. So here we are using a control step counter. It is going to count the number of clock periods, means the number of steps which are going to be executed. Each state or each count of this counter corresponds to one control step. The required control signals are the contents of control step counter, and next one is contents of the instruction register and contents of the conditional code flux and external input signals. Here external input signals means a memory function complete and interrupt request. So these signals comes under the external input signals. Again, insight into the structure of the control unit. So this is a simplified view of hardwired involved control unit. This one. Okay, here we have the decoder or encoder block. So this decoder or encoder block is a combinational circuit that generates the required control outputs depending on the state of all the inputs of a decoder or encoder block. Okay, and by separating these decoder or encoding functions, we will get this one. By separating the decoder and encoder block. So here both a decoder and encoder block are going to be separated. The step decoder provides a separate signal lines for each step or each time slot in the control sequence. Similarly, the output of the instruction decoder consists of separate lines for each mission instruction. So a decoder has separate lines for each steps, and also it will produces a separate lines for each and every mission instruction, separate output lines for each and every mission instruction. For if any instruction loaded into the instruction register. So here IR means instruction register. Instruction register holds the instruction which has to be executed currently. For any instruction loaded into the instruction register, then the decoder will set one of the output lines from INS1 to INS1. Okay, so whenever an instruction loaded in the IR register, instruction register, one of the output lines INS1 to INSN is set to 1. Okay, and the remaining all the lines are set to 0. The input signal to this encoder block. Okay, so all the is input signal. So from the step decoder, means here the the counter will count the number of clock pulses taken in order to execute a single instructions, and also from the decoder information, status flag information, condition code information, external inputs information. So all these input signal are going to be combined in order to generate the individual control signals. Okay, so in order to generate the individual control signals, this encoder will combine all the inputs. Okay, so means here all the individual control signals means see, each and every register has its own two control signals. Suppose Y in, PC out, add instruction, end of the information, or R1 in, R2 out. All these are the control signals. So all these control signals are either set or are reset by the decoder. So decoder will combine all the inputs and it will generate the corresponding control signals. So control signals means Y in, PC out, addition or end of the operation, or R1 in, R1 out, PC in signals, all the control signals. Okay, so as suppose for example I want the encoder has to generate the Z in control signal for the processor organization. Okay, now I want to generate the Z in control signals. Within a processor, we are having a Z temporary register. So it is used in order to store the ALU outputs. Okay, so now we are going to look the internal structure of the encoder. Encoder is a combinational, decoder and encoder both are combinational circuit. See, so in case of Z-in, we have these combinational circuit inside this encoder. Okay, so inside this encoder we are having this combinational circuit for generating the Z in control signal. Okay, so from this write the equation for Z in. Z in is equal to, we will get here it is an OR gate. Okay, means we will get a T1 plus T4 into branch instruction plus add into T6 plus and so on. Okay, so this is so here we are representing dotted means we are having a more circuit for Z in. Okay, this is for Z in control signal circuit which is present inside this encoder. The signal is asserted during a time slot T1 for all the instructions. During T6 for an add instruction. During T4 an unconditional branch instruction and so on. Okay, so this is this T1, T4, T6 are the time periods. And the logic function of Z in is derived from the control sequence. And now we will consider another example which generates end control signal. After a complete execution of an instruction, at the end we will get the end control signal. If end control signal is activated means the complete execution of the instruction is the complete execution of an instruction is completed. So and next we have to execute the another instruction. For this end control signal, the encoder contains this internal circuit. Okay, so this is the generation of the end control signal. This circuit also present inside the encoder. So for each and every control signal, we are having this type of combinational circuit, which is all these combinational circuits present inside the encoder. Okay, for this one the logic function will be AND is equal to T7, means T here also T7, T6, T5, T4, all these are the time periods. Okay, so T7 into add plus T5 into T5 into branch instruction plus T5 into N plus T4 into here T4 into N bar whole into branch instruction. Okay, so this is generation of the end control signal. This circuit also present inside the encoder. So like this way, so each and every control signal has its own combinational circuit. All these combinational circuits are present inside the encoder. Okay, so the encoder will generate the control signal by combining all the inputs. Okay, all the inputs means a decoder or counter inputs, next decoder inputs, and also external inputs, next conditional codes. By combining all these inputs, encoder will generate the corresponding control signals. For each and every control signal, we will have a combinational circuit which is present inside the encoder. And see here, in this circuit, we will have another control signal that is a run. When the run control signal is set to 1, causes the counter causes the counter to be incremented by 1 at the end of every clock cycle. Okay, so whenever the run is equal to 1, during that time the counter will be incremented by 1 at the end of each and every clock cycle. When this run control signal is equal to 0, it means the counter will stops counting. Okay, so this is needed whenever the wait memory function complete signal is issued to cause the processor to wait for the reply from the memory. These control hardware can be viewed as a state machine that changes from one state to another in every clock cycle, depending on the contents of the instruction register, the condition codes, and the external inputs. So depending on the instruction register, condition codes, external inputs, the control hardware is going to change its state from one state to another state for every clock cycle. The output of the state machine or the control signal. Okay, so the output of this state machine or the control signals. The sequence of operation carried out by this machine is determined by the by the wiring of the logic elements. Hence the name hardwired. Okay, so why we are giving hardwired means a sequence of operation carried out by this machine is going to be determined by the wiring of the logic elements. Hence the name is hardwired. A controller that uses this approach can be operate at high speed. However, it has a little flexibility and complexity of the instruction set it can implement is limited. Okay, so it has a little flexibility and the complexity of the instruction set it can implement is limited. Okay, so this is about hardwired control. So why we are using hardwired control means in order to execute the instruction the processor must generate some control signals. For a sequence execution of instruction, in order to generate these control signal, we are using hardwired control. So in a hardwired control, these control signals are going to be generated by the decoder and encoder blocks. These decoder and encoder blocks are also a combinational circuit. Inside an encoder, for each and every control signal, we will have a combinational circuit. Okay, so we have seen Z in control signal combinational circuit, at the same time end control signal combinational circuit. So like that we will have a different combinational circuits for different control signals. All these circuits will be present inside the encoder. Okay, so this is about hardwired control unit. And the next one is complete processor. So this is a complete processor. So inside a processor, we will also have the instruction unit, instruction cache, bus interface, integer unit, floating point unit, and also data cache. So along with instruction register, program counter, address register, data register, general purpose registers, control unit, ALU, and some of the temporary registers, along with these, the processor will also contain all these memory units. So this is a complete processor. This structure has an instruction unit. It fetches the instruction from the instruction cache. Okay, so the instruction unit fetches the instructions from the instruction cache or from the from the main memory. Okay, so this instruction unit fetches the instruction either from the instruction cache. If that instruction is not present in instruction cache, it will search the instruction in main memory when the desired instructions are not already in the cache. Okay, so the instruction unit that fetches the instruction from the instruction cache or from the main memory when the desired instruction is not already in the cache. It has a separate processing unit to deal with integer data and floating point data. Okay, so the processor has a separate processing units to deal with an integer unit to integer and floating point units. or floating point data. Each of these units can be organized as shown in this figure. A data cache is inserted in between these units and the main memory. Okay, so the data cache, here it is an instruction cache, it stores the instruction. Here it is a data cache, it stores the operands. A data cache is placed in between these two integer and floating point units and also in a main memory. Using separate caches for instruction and data is a common practice in many processors. Okay, so today or these days the processors uses these separate caches for both instruction and data. Other processors, maybe some type of processors, use a single cache that stores both the instruction and data. Okay, so in case of some of the processors, we will have a separate cache memory for instruction and data. Some type of processors contain the same cache memory in order to store the instructions and data. The processor is connected to the system bus and hence to rest of the computer by means of a bus interface. Okay, so the processor is connected to the system bus and hence to the rest of the computer system, means a memory, input output device or any peripheral devices by means of a bus interface. Although we have shown just one integer and one floating point. Okay, see here we have showed one integer unit and also one floating point unit. Maybe some processors include several units of each type. So maybe some type of, in this figure we have shown only one integer unit and one floating point unit. But some of the processors may include several units of each type to increase the potential for concurrent operation. So the processor will increase several units for integer and floating point units in order to increase the potential for concurrent operation. The way in which multiple units can be organized to increase the rate of instruction execution. So in this way, so by using multiple units, we will increase the rate of instruction execution. Hence, the system speeds will get increases. Hence, automatically the performance of the system will be better by using multiple units. Okay, so this is a complete processor. So within a processor we are having instruction unit, integer unit, floating point unit. For storing instructions we have instruction cache, and for storing integer and floating points data we will have a data cache. Within an instruction cache we will store the instruction, the data cache will store the operands. So the processor is going to connected with the system bus and also the external memory. The processor will connect with the system bus and the external and the rest of the devices in the computer by means of a bus interface. Okay, so this is a complete processor. And in next lecture we will discuss about microprogrammed control. Okay, so in order to generate the control signals we are using hardwired control and also microprogrammed control. So hardwired control is over, and in next lecture we will see about microprogrammed control. Okay, thank you.